All right, so I'm going to say a little bit about Sidon sets for linear forms. So in arithmetic, we like the idea of adding integers. So if you have a set A of integers, the twofold sum is everything of the form A1 plus A2. And if you get carried away, you can look at H-fold sums. It's the sum of all, it's the set of all sums of H, not necessarily distinct elements of A. And what we call a basis of order H is a set A whose sum set contains, if A is a set of non-negative integers, it contains every non-negative integers, or sometimes you look at asymptotic bases where the H-fold sum set contains all sufficiently large numbers, or sometimes asymptotic bases in the sense that the sum set contains all non-negative integers except for set of density 0. And we often want to know how many ways you can write a number as a sum of H terms from the set. And one representation function is this lowercase r of n. So it's the number of H tuples of elements of A in increasing order that sum to n. And so to say you have a basis of order H means that every number has at least one representation as the sum of H elements from the set A. And one of the most famous unsolved problems in additive number theory is the question of Erdős and Turan, which is to prove or disprove, because no one knows what the answer is, that if you have any basis of order H, its representation function has to be unbounded. This really is one of the major problems that's been around for almost 100 years. So an equivalent way of saying that is that if you have a set A of integers and RAH of n is the representation function, if the lim-inf is positive, then the lim-sup is infinite. This is what's sometimes called the Erdős-Turan conjecture. So a Sidon set is in a sense the opposite of a basis. So in a Sidon set, the number of representations is not greater than or equal to 1, it's less than or equal to 1. So every number has at most one representation as a sum of two elements of the set A. Or if you're looking at H-fold sums, a Sidon set of order H is a set of integers where every number has at most one representation as a sum of H elements from the set A. So there are a lot of open problems about Sidon sets. In some sense, almost every problem is open. So if you let F2 of n be the largest subset that is a Sidon set and contained in the interval from 1 to n, then we know that F2 of n is asymptotic to the square root of n. Erdős asks if in fact F2 of n is always within a constant of root n. And questions like this are still mysterious. So what I am doing is just looking at the analog of a Sidon set for a linear form. So a linear form is a function that looks like this: C1x1 plus C2x2 up to CH x sub h, where these coefficients C sub I are integers. And if you take a set of integers A, negative or non-negative or positive, doesn't matter, you look at the image of the set A under phi, just everything, every number that's represented by phi, by this linear form phi. And so that's what we're interested in. This, you have the linear form, you have a set A of integers, and you look at this image, which you can also describe as a sum of dilates. And some people like to do that. If you take the simplest linear form, where all the coefficients are 1, x1 plus x2 plus x3 up to x sub h, then the image is just the usual H-fold sum set. Associated to a linear form, we have this representation function for which I'm using a capital R, not a lowercase r. So this is a set of H tuples of elements of A, such that phi of A1 up to AH equals n. And In the case when these are integers, these are not necessarily in increasing order. So we're really looking at H tuples, all H tuples. So this is actually a little bit different from what you do when you're looking at Sidon sets in the classical case. Just to say something about these linear forms, we say that A is a phi basis for almost all integers, or you can say for all integers, but in this case, for almost all integers, if the set of numbers that, if every number except for a set of density 0 can be represented by this linear form. So that's what we mean by a phi basis of order H. And if you have such a thing, then the representation function is 0 only on a set of density 0. So the representation function is some function from z to the non-negative integers together with infinity, because some numbers can have infinitely many representations. But it has the property that f inverse of 0, this is the set of numbers that cannot be represented by the form, has density 0. And there's a general question, given a linear form, what might be called the inverse problem for bases is to determine if you have such a function. So you have a function from the integers to the non-negative integers union infinity, and f inverse of 0 has density 0. Can you actually find a set A for which this function f is its representation function? And if there does exist such a set, can you actually construct it in some sense? So in the first case that you would normally look at, binary linear forms, there's the following result. This is an old result. If you take a linear form in two variables, C1 and C2, with non-zero coefficients and coefficients that are relatively prime, which satisfy just the following conditions, C1, C2, the product is not +1, not -1, and not -2, then for any function f, there exists, with this property, f inverse of 0 has density 0, there always exists a set A of integers for which the representation function of the set A is equal to f. And in particular, if you choose a function f which is identically equal to 1, then you get the very nice result that except when C1, C2 is +or -1 or -2, there always is a what you might call unique representation basis. That is, every number can be represented and every number is represented exactly once. So that is a kind of Sidon-like property, perhaps. What about Sidon sets for linear forms in general? So you take a field f. So I don't want to restrict myself to the integers or even to rational numbers, just because the theorems hold have a kind of structural generality to them. So you have a field f, and you look at a linear form with coefficients in the field. You take a vector space over the field and a set A of vectors, and A to the H is the set of all H tuples of your vectors, and the image, the phi image of A, that just means all the vectors that can be represented as phi of A1 up to AH, where the A1 up to AH are elements of this set A. So, you can take the field to be the rationals and A to be the set of integers, and that's the classical number theory setting. We say that a subset A of this vector space is a Sidon set for the linear form phi if it has the following property. If you take two H tuples, A1 up to AH and A1 prime up to AH prime, the only time phi of A1 up to AH equals phi of A1 prime up to AH prime if the two H tuples are the same. And just to make, the direct question is, if you're given a linear form, what are the Sidon sets for that linear form? Now, let's start with the most trivial thing. If you take a set with just one element, it's a Sidon set for everything, because there's only one H tuple. You have this, there's like nothing else. So every set with one element is a phi Sidon set. And you might ask, well, okay, that's not so exciting. what about a set with two elements? Can you find a two-element set, which is a sit-on set for your given linear form phi? And the answer is sometimes yes and sometimes no. So there is a simple obstruction to the existence of a phi sit-on set for a linear form. Namely, it's the following. So you have this linear form with coefficients C1 up to C sub h. And for every subset I of this set of integers from 1 to 8, you have the subset sum. So S of I is the sum of the coefficients C sub I for I in the set capital I. And you let S of the empty set be 0. So suppose for your linear form, you have two disjoint subsets, I1 and I2, of coefficients, which have the same subset sum. So you have I1 and I2, which are disjoint, and everything else that's called I3. So suppose you have a set A that has at least two elements. So you can pick U and V in this set, which are different, and W can be equal to U or V, it doesn't matter. But U and V are different. And you construct two H tuples in the following way. For in the set I1, you let AI be U. In the set of primes, you let AI prime be V for I and I1. For I and I2, you reverse it. The AIs are V and the AI primes are U. And for everything else, it's equal to this number W. So these are two distinct H tuples because these two sets are, the union is not empty and they're disjoint. And you do this calculation, and phi of A1 up to AH is the sum of CIAI for the I's in I1 and CIAI for the I's in I2. But in I1, the AIs are all U, and in I2, the AIs are all V, and these guys are all W. But the sum of I and I1 of CI is the same as the sum of I and I1 and I and I2 of CI. That we had these two equal subset sums. So you just switch these two things and rearrange it, and you get that phi of A1 up to AH is phi of A1 prime up to AH prime. So A is not a sit-on set. So if your linear form has this property that you have disjoint sets of the coefficients of the form and the subset sums are equal, there cannot be a sit-on set which has two or more elements. And that turns out to be the only obstruction to the existence of a sit-on set. So it's a kind of negative property N. A form has this negative property if there do not exist disjoint subsets I1 and I2 of 1 up to H that have the same subset sum. And yeah, so for example, if you take this linear form 1 times x1, 2 times x2, 4 times x3, and so forth, just the powers of 2, the subset sums are distinct. So this doesn't, so this has this property N. And the theorem says the following: if you take a field F, and again, take the rationals, let V be a vector space over F, or you can let V be the rationals. Let X be an infinite subset of the rationals. You can let X be the integers. And you take a linear form with non-zero coefficients, and coefficients can be rationals or integers. The following are equivalent. Well, X contains an infinite sit-on set. Well, 1 implies 2 isn't hard. 2 is X contains a set with at least 2 elements. 2 implies 3. If X contains a set with at least 2 elements, then it has this negative property N. And then the key thing is that the converse holds, that if X has this negative property N, then there exists an infinite phi sit-on set for the set. So that gives you a kind of a necessary and sufficient condition for a phi sit-on set to exist. Now you can ask, you can ask lots of things. For example, how common are sit-on sets? So on your field, you have, let's say you have a field with an absolute value. So it can be the usual absolute value on the rationals or the reals or the complexes, or a p-adic absolute value, just some function that satisfies, it's non-negative and multiplicative and satisfies a triangle inequality. the usual definition of an absolute value on a field. It's trivial if every non-zero element has absolute value 1, and it's non-trivial otherwise. And if you have a non-trivial absolute value on the field, you can show right away that the field has to be infinite. And in fact, the inf of all the non-zero, the absolute values of the non-zero numbers is 0. So you can get as close to 0 as you like in absolute value. And when you have an absolute value on a field and you take a vector space over the field, you can have a norm on the vector space with respect to the absolute value. It's the usual definition of a norm, non-negative and homogeneous, and satisfies a triangle inequality. So suppose you have a field F with some non-trivial absolute value, and you take a vector space over F that's a norm with respect to the absolute value. So n is the set of positive integers, and you take two sequences of vectors, a sequence AK and a sequence BK of vectors. They don't have to be distinct. And you let epsilon k be an infinite sequence of positive real numbers. So we say that the sequence A is an epsilon perturbation of the sequence B if the, so these are vectors, so you can look at the norm of the difference between the corresponding vectors in the two sequences. So an epsilon perturbation is when the norm of the difference AK minus BK is less than epsilon k for all k. And so one has the following theorem. You take a field with a non-trivial absolute value and a vector space that's normed with respect to the absolute value. You take any sequence epsilon of positive real numbers, and you take a linear form phi with coefficients in F for which Sidon sets exist. That means that this linear form satisfies this property n. If you take any set of vectors B in the vector space, you can always find a phi Sidon set of vectors such that AK minus BK is less than epsilon k for all k. In other words, for any epsilon, you take any set of vectors and there's always an epsilon perturbation of your arbitrary sequence of vectors, which is a phi Sidon set. And if you just let your epsilons go to 0, this just says that for any set of vectors in your vector space, there's always a phi Sidon set that's asymptotic to your this given set of vectors. So that's kind of curious. Now, this is just a general nonsense statement about arbitrary absolute values. So, you know, if you take your favorite absolute value, I mean, mine's the p-adics. So, so suppose this is the usual p-adic absolute value on the rationals with norms, so that it doesn't matter how it's normed, but the absolute value of p is 1 over p. You have the following theorem. So phi is a linear form with rational coefficients that satisfies this property n. Epsilon k is any sequence of positive real numbers. Pk is any sequence of prime numbers. And now someone gives you a sequence of integers, bk. So the theorem says there exists a strictly increasing sequence of positive integers, right? These integers don't have to be positive and they don't have to be different, but there's a strictly increasing sequence of positive integers, a sub k, which is a phi Sidon set with respect to this linear form. And pk, so ak minus pk, p-adically is less than epsilon k, not just for one prime p, but for all the primes, but for the first k primes in your sequence. Which means in particular that AK is p-adically asymptotic to BK simultaneously for every prime. It's like, so it's not just a p-adic approximation for one prime, but it's a p-adic approximation for all primes. And this is just says the same thing. If you take your your epsilon k is going to 0, for every prime number p, you have a set A p-adically asymptotic to B in the sense that AK minus BK, the p-adic value goes to 0. Again, for all primes. That's really kind of nice. There are constructions of phi-Sidon sets. There's a kind of congruential construction. This is, but let's go back and look at what is the more traditional question about Sidon sets, which is how big they can be. So for a classical Sidon set of integers, the counting function a of x, the number of elements of your set up to x, is like at most x to the 1 over h, and you can do at least x to the 1 over h with the right construction in the finite case. For the infinite case, it's really this very important phenomenon. On the one hand, Erdős constructed an infinite Sidon set. This is not for a linear form. This is the traditional Sidon set for a1 plus a2 of integers, where the lim sup of a of n over root n is positive, bounded away from 0 and at least a half. But he also proved that if you take any infinite Sidon set, that it can't be always bounded away. It can't be that a of n over root n is always bounded away from 0, that the lim inf of a of n of like root n over log n is always less than some positive constant. This is really a very interesting phenomenon, and recently there have been a number of papers written about this in a variety of contexts. So you can give simple estimates for the size of Sidon sets for a linear form. If you have a field with an absolute value, the counting function of a set x just counts the number of elements x whose absolute value is at most t. And you can get the same kind of essentially trivial upper bound for the size of a Sidon set for a linear form. You have a field with an absolute value. So these CIs there's a number C, which is the sum of the absolute values of the CIs, and any Sidon set in the field with respect to this linear form will have a counting function that grows no faster than it really can, like the 1 over 8th root. And there are various constructions, but I just wanted to mention one last thing. So, there was this guy, Charles Darwin. He was the great man of 19th century biology. And his last book was on the movement of plants. He wanted to know how plants could move. People used to think that the difference between an animal and a plant was that an animal moved, but a plant didn't. And there was even a question, and there still is, whether the growth of plants can be affected by music. So if you play music in front of your plant, does it grow better or worse? And people try this with classical music, with rock and roll, with all sorts of things. But Darwin also tried this, and it wasn't so much that he thought there would be a positive result, but unless you do the experiment, you don't know. That's the whole idea. So some things you want to try. So this is in this category of playing a music in front of a plant to see what happens. Suppose you take a field F and a linear form. So let's say the linear form is monic if this first coefficient is 1. And say a subset of the field is normalized if it contains 0 and 1. So the direct problem for Sidon sets is the following. If I give you a form, describe the Sidon sets. Right? So that's what you do in classical Sidon sets. You have the form is x1 plus x2, describe the Sidon sets. But you could ask the inverse problem when you're looking at linear forms. If you're given a set A in your field, what are the linear forms for which the set A is a Sidon set? And we can start by looking, you only have to look at monic forms, and you only have to look at normalized sets. So you can assume that the first coefficient in the form is 1. And and binary forms, that's the first thing to look at also. So your form is x1 plus c times x2. So every binary linear form that's normalized is just determined by this coefficient c, which could be 0. I don't know why I put a star there, but it could be 0 times x2, I guess. And if you're given a set A of the field, you can ask, what are all the forms or all the numbers C for which A is not a phi-Sidon set, right? For example, is it finite or infinite? And here is something in the way of an answer. So if you have a set A in the field, the difference set is the set of differences, and the set of quotients of differences, that's this D star of A. So this is everything D prime over D, where D and D prime are differences, and the denominator isn't zero. So you can show that, first of all, if A is a non-empty subset of the field, finite or infinite, the exceptional set, this means the linear forms for which A is not a Sidon set, is always contained in this quotient set. And in particular, if your set A is finite, then D is finite. So every non-empty finite subset of the field is a phi-Sidon set for all but finitely many binary forms. And you can actually compute this exceptional set explicitly. I mean, you can, for as big as you want. It just depends on how long you want your computer to run. I mean, 2, 3 you can do by hand. So if you take a non-zero number C, E of C is this set with plus or minus C plus or minus 1 over C. So unless C is plus or minus 1, this has 4 elements. And you can show that if C is an exceptional number, then all 4 of these numbers are exceptional. And then you can actually make a list. Like, so for sets of cardinality 2, they're just 3 exceptional linear forms, binary linear forms. And if you take a set of cardinality 3, it's normalized, so 0, 1, and something else. These are exactly the exceptional binary linear forms. And it's actually kind of interesting. It looks like this. And if you think of these things as they correspond to SL2Z matrices, it's actually quite interesting to look at these. And if you take a set with 4 elements, 0, 1, A, and B, the finite number of exceptional binary forms for which this set A is not a Sidon set, they can be listed here. In any case, all of this is in preprints on arXiv, and I thank you very much for your attention. So let me stop share, and I'm done. And the next talk is in a couple of minutes.